Hi, my name is Clonan. I'll be presenting our project Insights from the use of phycoerythrin and phycocyanin sensors in freshwater algal monitoring. I've worked on this project with my coworkers at the New Jersey Water Supply Authority, Melissa Mazzaro and Heather Desko, as well as our partners at the New Jersey Department of Environmental Protection, Eric Ernst and Dr. Rob Newby. So my organization, the New Jersey Water Supply Authority, is a state organization managing 3 reservoirs and a canal for raw drinking water supply. Current contracts provide water for approximately 2 million residents across central New Jersey, and today we'll be focusing on monitoring conducted at the Manasquan Reservoir, whose 62 square mile watershed above the pump storage intake is highlighted here. While water pumped from the Manasquan River is responsible for most of the reservoir's fill, there's an approximately 3 square mile direct watershed to the reservoir consisting of these 4 wetlands, which are connected to the reservoir through overflow culverts. The 770-acre Manasquan Reservoir has a capacity of 4.7 billion gallons and a max depth of 51 feet. The reservoir typically mixes twice per year with cyanobacteria blooms often occurring alongside fall destratification. The reservoir is managed by the Monmouth County Park System for trails, fishing, and boating, and water pumped into the reservoir and taken out from the reservoir all goes through the inlet-outlet tower on the east side by the dam. The reservoir is about 40 feet deep here at full pool, and we'll be focusing on samples taken here today. So just some background on the 2 pigments we'll be focusing on today. Most freshwater scientists are familiar with phycocyanin, the blue-green pigment that has become a biomarker for cyanobacteria. Typical freshwater cyanobacteria often associated with phycocyanin include Aphanosomnom, Dolichospermum, which is pictured below, as well as Microcystis and Osculatoria. Meanwhile, phycoerythrin is a red-colored pigment found in some cyanobacteria, cryptophytes, and red algae, which has been historically more often used in marine harmful algal bloom monitoring for red tides. Some literature has found it can be useful for freshwater monitoring, as some cyanobacteria specialize in phycoerythrin, such as Planktothrix, which is pictured here with more of the red pigmentation on the right, as well as Synechococcus. Starting in June of 2023, we've been collecting samples for different phosphorus and nitrogen compounds at various points across the center of the reservoir, as well as at the boat launch. Each of the open water sites are sampled at 3 depths: the surface, the thermocline, and 1 meter off the bottom sediment, which I'll often refer to as the bottom sample from here on out. We find the thermocline during each sampling event by conducting a full vertical profile of the water column with an in situ meter for dissolved oxygen, temperature, pH, and fluorescent-based phycocyanin, phycoerythrin, and chlorophyll. The thermocline was typically 4.5 meters below the surface, which is about half the water column. Because of this, during destratified sampling dates in the winter, the thermocline samples were taken at the typical 4.5 meter depth. However, only at the IO tower sites, which is the red dot on the right here near the dam, have we also been collecting samples analyzed for phytoplankton assemblages. Here, the bottom sample was typically 10 to 11 meters deep, about 1 meter off the bottom sediment, depending upon the level of reservoir fill. As background, this graph shows total cyanobacteria counts throughout the study period from our 3 depths. The solid line represents counts from the surface water, the dashed line represents counts from the thermocline, and the dotted line represents counts from the bottom sample. The points are all represented by different symbols. These symbols are representing the most abundant cyanobacteria genera in each sample. We see that for most of the sampling dates, total cyanobacteria counts were fairly within range of each other throughout the 3 depths, particularly during the winter months when the water column was destratified. However, Aphanosomnon was most often the dominant genera, particularly in the thermocline and surface samples, and especially during the winter of 2023 to 2024, when we saw an Aphanosomnon surface water bloom upwards of 1 million cells per milliliter. We also have some dates at the surface and thermocline dominated by Dolichospermum, particularly in the summer and fall of 2024. During stratified periods in the summer of 2023 and 2024, we also see that the bottom samples were dominated by Planktothrix. The nutrient levels we've observed were typically low, often with non-detects for ammonia, nitrate plus nitrite, and orthophosphate. All nutrients seem to feature their highest ranges in the bottom samples, where nutrient concentrations were typically increasing throughout the summer while the reservoir was stratified. Total phosphorus was often below the NJDEP surface water standard for lakes of 0.05 milligrams per liter, but there were a few dates where nutrients were excessive. So now that we've painted the picture of typical cyanobacteria communities and nutrients at the Manasquan Reservoir, we'd like to evaluate how the field readings of phycocyanin and phycoerythrin match with this data, mainly by investigating 1, if phycoerythrin is adding any value missed by phycocyanin, and 2, if there are certain cyanobacteria genera more associated with phycoerythrin than phycocyanin. So first I want to note that we're looking at each of these fluorescent-based readings in micrograms per liter, and that each of the pigments have their own scale and ranges. The first thing to notice is that in phycoerythrin, we seem to have a greater separation of readings between the 3 depths, where we see these wider ranges, and highest readings on any given date are almost always matched with the bottom samples, represented in yellow, which are dominated by Planktothrix. Meanwhile, phycocyanin readings on the middle graph are typically close to each other among all 3 sampling depths, with the highest readings often occurring at the thermocline, represented in red. A couple of exceptions to this are the January 2024 aphanizomenon bloom, as well as the summer of 2024, when the highest density among any depth was found at the bottom, here in yellow, and dominated by Planktothrix. So while phycoerythrin seems to have caught the jump in Planktothrix counts slightly earlier, building throughout the spring and into the summer, phycocyanin still caught an increase of Planktothrix and an increased cell density at the bottom, though it was a little bit later and not as pronounced as the depths or differences between the readings at the different depths for phycoerythrin. I also included chlorophyll here in the bottom graph because it comes with the fluorescent-based sensors, but it doesn't really seem to overlap with phycocyanin or phycoerythrin in our sampling data. Now, if we separate the pigment readings, matched with the most abundant cyanobacteria genera in each sample, we see that the highest PE readings are often associated with Planktothrix. We also see that phycocyanin seems to be a little less genera-specific, as the ranges for phycocyanin are pretty much even throughout all of the different genera that were the dominant taxa in our samples. While interestingly, higher chlorophyll readings seem to be slightly more associated with aphanizomenon and cyanogranus. Now, doing the same for nutrients, we see that the highest ammonia concentrations are associated with Planktothrix, and otherwise ammonia is near or under the detection limit when in samples dominated by other genera. This is likely because Planktothrix is dominant in the bottom samples, especially in the summer, when ammonia concentrations are increasing due to the decomposition of detritus on the sediment and a lack of mixing in the water column. This also contributes to Planktothrix dominating in samples with higher total nitrogen. Meanwhile, there isn't enough data here to truly call it a trend, but it is interesting to note that samples with more nitrate-nitrite, including these 3 dates of outliers with much higher concentrations, all seem to be dominated by aphanizomenon. Now, in order to put this all together, I think it would be helpful to focus on the benthic growth of Planktothrix during the past year. In the top graph, we see the Planktothrix cell densities increase throughout the spring and the summer, and then decrease in the fall around destratification in October. Underneath this, in the second graph, we see ammonia increasing throughout the spring, stabilizing in the summer, as it is consumed by the growing Planktothrix population, and then peaking in October following destratification and Planktothrix die-off. In the third graph, phycoerythrin is following nearly the same curve as Planktothrix cell density. But on the bottom, benthic phycocyanin also rises and falls with Planktothrix cell density and phycoerythrin readings. However, we then see phycocyanin increase again in October, post the destratification, when cell counts for Planktothrix had decreased and the dominant genera at the bottom was Dolichospermum. So in summary, phycoerythrin does seem to help distinguish Planktothrix density compared to other dominant taxa we've seen at the Manasquan Reservoir, such as Aphanizomenon, Dolichospermum, Cyanogranus, and Aphanicapsa. Meanwhile, phycocyanin is likely still a more reliable catch-all for all cyanobacteria genera. It will be important for us to continue to monitor phycoerythrin peaks in the field as it can serve for a proxy for Planktothrix density. And this is important because Planktothrix is a known producer of cyanotoxins. So thank you very much for watching my presentation. I hope to see you at the conference, and if you are attending virtually, I'm happy to answer any questions through email. Thanks again and have a great day.